Deep inside some of America's most secure heavy manufacturing facilities, giant blocks of specialty steel are transformed into one of the most demanding precision components in modern defense engineering. These are cannon barrels, massive tubes designed to withstand extreme pressure, intense heat, violent recoil forces, and microscopic tolerance requirements over years of service. To most people, they look simple from the outside, just long cylinders of steel. But the reality is far more complex. Behind every finished barrel is a world of forging presses, giant machine tools, heat treatment furnaces, advanced metallurgy, and inspection systems operating at astonishing scale. Today, we're stepping inside the supergiant cannon barrel factory, where America builds massive precision systems through one of the most specialized manufacturing processes in heavy industry. The story begins with steel. Not ordinary construction steel, not generic industrial metal. Cannon barrels require advanced alloy steels engineered for strength, toughness, fatigue resistance, and dimensional stability. These materials must survive repeated stress cycles while maintaining internal precision over time. That means the process starts long before machining. Steel producers melt carefully selected raw materials in controlled furnaces, blending alloying elements to create exact metallurgical properties. The molten metal is then cast into large ingots or billets weighing many tons each. From there, the material heads to forging operations, and this is where the scale becomes impossible to ignore. Inside forging shops, glowing steel billets are heated to extreme temperatures until they become workable. Overhead cranes lift them from furnaces and place them beneath giant presses capable of delivering enormous force. Each strike reshapes the metal. The goal is not only to form the outer shape, but to refine the internal grain structure of the steel. Proper forging improves strength, toughness, and reliability. Critical qualities for components subjected to repeated stress. Slowly, the rough form of a barrel blank begins to emerge. Long, thick, and immensely heavy, it still looks nothing like a finished precision component. After forging, the blank cools under carefully controlled conditions. Then it moves into rough machining. Large industrial lathes grip the steel between supports and begin cutting the outer surface. Massive cutting tools shave away excess metal while operators and automated systems monitor dimensions continuously. Sparks fly, steel curls into long ribbons. Hours of machining may remove hundreds of pounds of material. The outer geometry is only part of the challenge. The interior must also be created with extraordinary accuracy. That requires deep hole boring. Specialized machines gradually open and refine the internal passage through the center of the barrel blank. This process must remain perfectly aligned over long distances. Even tiny deviations matter. Coolant systems circulate constantly. Sensors monitor vibration, temperature, and tool wear. The machine advances slowly because precision matters more than speed. Once the internal bore reaches target dimensions, the barrel enters another critical stage: heat treatment. This is where metallurgy and engineering meet. Large furnaces heat the steel under tightly controlled conditions, then cooling cycles are applied to achieve desired hardness and toughness. Depending on the design, multiple heat treatment stages may be used to optimize final performance. Without proper heat treatment, even perfectly machined steel may fail under stress. With it, the material gains the balance of durability and resilience required for demanding service environments. After heat treatment, the barrel often returns to machining. Why? Because heating and cooling can cause minute dimensional changes. Final machining restores exact tolerances on mounting surfaces, alignment zones, and outer geometry. At this stage, giant grinding and finishing systems may refine surfaces even further. Smoothness, straightness, and concentricity are carefully verified. Then comes one of the most important phases in the entire factory: inspection. To the public, inspection sounds simple. Inside advanced manufacturing, it is an industry of its own. Technicians use precision gauges, alignment tools, laser systems, ultrasonic testing, and non-destructive evaluation methods to inspect the component without damaging it. Only barrels meeting strict standards move forward. Some may undergo corrective finishing. Others may be rejected entirely. Because when tolerances are measured in tiny fractions, quality cannot be guessed. It must be proven. Modern factories increasingly rely on digital systems to support this work. Production data follows each component through the plant. Material origin, furnace cycles, machining history, inspection records, and process measurements can all be logged. This creates traceability across the entire manufacturing journey. If a future issue is ever discovered, engineers can review exactly how that component was made. That level of accountability is common in aerospace and defense manufacturing, and cannon barrel production is no exception. But giant machines alone do not run these factories. Skilled workers remain essential. Metallurgists study steel behavior. Machinists manage complex setups. Engineers optimize production flows. Maintenance teams keep high-value equipment operating reliably. Inspectors verify standards no machine can assume on its own. In many facilities, this knowledge has been built over generations. Experience matters. Heavy manufacturing also demands logistics on a massive scale. Raw steel arrives by truck or rail. Forged blanks move between departments using cranes. Finished components may require specialized transport due to length, weight, and handling sensitivity. Entire buildings are designed around movement of oversized precision parts. Even the floor layout reflects the product. Wide aisles, reinforced foundations, crane rails, and high base ceilings all exist because ordinary factory design would not be enough. And while these factories are associated with defense systems, they also represent something broader: advanced industrial capability. The same expertise used in giant forging, precision boring, metallurgy, and inspection supports many sectors, including energy, aerospace, transportation, and heavy equipment. That is why facilities like these are strategically important beyond a single product line. Technology continues pushing the industry forward. Computer-controlled machining improves repeatability. Digital twins help model tolerances before cutting begins. Predictive maintenance reduces downtime on expensive equipment. Turning a giant block of steel into a long, precise, durable barrel is still one of the hardest manufacturing challenges in heavy industry. They may hear about defense systems in headlines, but not the factories where giant steel components are forged, bored, treated, measured, and perfected. If you enjoyed this deep dive into one of the most specialized factory systems in the world, make sure to like the video, subscribe to the channel, and hit the notification bell so you never miss our next look inside the giant industries shaping modern life. Thanks for watching.
Every modern battlefield depends on a machine that combines power, protection, and precision. The main battle tank, designed to move over rough terrain, withstand enemy fire, and deliver devastating firepower, it is one of the most complex land vehicles ever created. But behind every tank rolling into action lies an extraordinary story, one of metallurgy, mechanics, and military-grade engineering. From hardened steel plates to multi-ton rotating turrets, each component must be crafted with extreme precision to survive the world's harshest conditions. In this documentary, we go inside a cutting-edge defense manufacturing facility to uncover how modern tanks are made. You'll witness how raw metal is forged into armor, how engines with over 1,500 horsepower are assembled, and how advanced electronics give these giants their strategic edge. This is not just about machines, it's about mastery. Let's explore how tanks are built, from armored plates to battlefield powerhouses. Every tank begins with its most critical feature, armor. Unlike ordinary steel, the plates used in tank construction are engineered to withstand high-velocity impacts, extreme temperatures, and explosive forces. The process starts with specialized armor-grade steel, known as rolled homogeneous armor. This high-strength alloy is made by melting iron ore with carbon and other elements like manganese, chromium, or nickel, depending on the required ballistic properties. The molten steel is poured into molds, then rolled into thick slabs under immense pressure to refine its grain structure and eliminate internal flaws. These slabs are then cut and shaped using plasma cutters and CNC machines to match the tank's unique dimensions. At this stage, the steel might undergo heat treatment, a series of controlled heating and cooling cycles, to enhance its hardness without compromising ductility. To increase strength without adding excessive weight, the armor is often assembled in layers, combining different materials such as ceramics, composite panels, or explosive reactive armor, ERA. These modular layers are precisely engineered to absorb, deflect, or disrupt incoming projectiles. Robotic welding arms are used to assemble the main hull. Precision is vital. The seams must be strong, but also smooth, to reduce weak points and maintain structural integrity. Once the structure is formed, the entire shell undergoes non-destructive testing. Ultrasonic and X-ray inspections reveal internal defects. Impact testing ensures resistance to simulated battlefield conditions. Only after passing all tests does the armored hull proceed to the next phase, becoming the mobile foundation of a fully operational battle tank. With the armored shell completed, attention turns to the foundation that gives the tank its mobility and power: the hull and powertrain. The hull is the lower portion of the tank, housing the driver's compartment, fuel tanks, transmission, suspension system, and the engine bay. Engineers begin by fitting internal structural supports into the armored shell. These supports add rigidity and create defined zones for each system. Next comes the installation of the powertrain, a powerhouse capable of moving a 60-plus ton vehicle across mud, sand, or rubble. Most modern battle tanks, such as the M1 Abrams, use either a 1,500 horsepower gas turbine engine or a turbocharged diesel engine. These engines are pre-assembled in a clean room, then carefully lowered into the hull using an overhead crane. Connected to the engine is a heavy-duty automatic transmission designed to handle massive torque while offering multiple gear ratios for both combat and cruising. This transmission is coupled to a drive shaft system that channels power to the drive sprockets located at the rear of the tank. Suspension is another critical system. Tanks use torsion bar suspension or hydropneumatic systems to absorb shocks from uneven terrain. Each road wheel is attached to a torsion bar, which flexes under load, providing a smoother ride for both the crew and the sensitive electronics inside. The wheels are then connected to the track system, made from interlocking metal segments with rubber pads. Tracks are assembled on-site, then stretched around the drive sprockets and road wheels. The result? A continuous loop that distributes the tank's weight evenly, allowing it to traverse almost any surface. Once assembled, all mechanical systems undergo extensive bench testing. The engine is started, transmission cycled, and tracks rotated at various speeds. Engineers monitor oil pressure, temperature, and vibrations to detect any early faults. Only when the tank's mobility systems pass every test does it advance to its next evolution, receiving the firepower that defines its battlefield presence. If the hull is the backbone of a tank, the turret is its muscle, housing the firepower, optics, and targeting systems that define the tank's combat capabilities. Construction of the turret begins with a circular armored shell, fabricated from high-strength steel and composite armor. Just like the hull, its walls are designed to deflect or absorb the kinetic energy of incoming rounds. Advanced tanks may also include explosive reactive armor, ERA, panels, which detonate outward to neutralize incoming projectiles. The heart of the turret is the main gun, usually a smoothbore cannon ranging from 120mm to 125mm in diameter. Made from high-grade steel, the barrel undergoes precision forging and rifling if required, followed by stress relief heat treatments to ensure durability and accuracy under extreme pressure. The cannon is mounted on a gun cradle, which connects to the elevation and recoil systems. These allow the barrel to move vertically and absorb shock during firing. Below the cradle is the autoloader system, used in many modern tanks to automatically chamber shells from a rotating magazine, increasing rate of fire and reducing crew size. Surrounding the gun is an array of advanced optics and targeting systems. These include thermal imaging cameras for night and low visibility conditions, laser rangefinders to calculate target distance with extreme precision, ballistic computers that account for wind, movement, and angle of fire. These components are wired into the tank's fire control system, FCS, which calculates the optimal firing solution in milliseconds. Many modern turrets are also equipped with stabilizers, allowing accurate fire while the tank is on the move. The turret is mounted onto the hull via a turret ring, a reinforced bearing system that allows full 360-degree rotation. Heavy-duty motors power this rotation, controlled from within the crew compartment. Once all internal components are fitted, the turret is hoisted by crane and carefully aligned with the hull. Final calibrations ensure that electronics, hydraulics, and mechanical linkages are perfectly synchronized. With the turret in place, the tank is now a fully armed combat machine, ready for battlefield testing, but not yet complete. Next comes the nerve center, electronics and control systems. While steel and firepower give a tank its strength, it's the electronics and control systems that give it intelligence and precision. Inside the armored shell, a network of advanced electronic modules manages everything from targeting to navigation. At the heart of this system is the fire control computer, a ruggedized processor that takes real-time input from sensors, rangefinders, gyroscopes, and environmental data to calculate the perfect firing solution in fractions of a second. The gunners and commanders' stations feature multifunction displays, joystick controls, and high-resolution targeting optics. These are linked to thermal and infrared cameras, allowing the crew to detect threats in complete darkness through smoke or in adverse weather. Navigation is handled by an integrated inertial navigation system, INS, combined with GPS, giving the crew precise awareness of location and terrain. This is essential for coordinating with allied units and avoiding known threats in the battlefield. Communication systems are also critical. Each tank is equipped with secure digital radios, allowing encrypted voice and data exchange with other vehicles and command posts. Some platforms even support network-centric warfare, linking into larger battlefield networks for real-time intelligence sharing. To manage all these systems, the tank features a central power distribution and control module, ensuring that electrical loads are balanced and protected. Backup batteries and redundant wiring prevent system failure during combat. Modern tanks may also integrate active protection systems, APS, using radar, cameras, and microprocessors to detect and neutralize incoming projectiles before impact. Once installed, all electronics undergo diagnostic tests to ensure accuracy, synchronization, and combat readiness. With electronics in place, the tank is nearly complete. What follows is a crucial test of everything working together. Real-world trial runs. Before a tank can be deployed, it must prove itself through rigorous testing, both in the lab and in the field. The completed vehicle is first subjected to static inspections. Technicians check wiring integrity, fluid levels, weapon alignment, and system calibration. The turret is rotated, the gun elevated, and all hatches operated to ensure mechanical soundness. Next, the tank is moved to a test track, a simulated battlefield environment with mud, water obstacles, steep inclines, and rocky terrain. Here, the engine is pushed to full power, the suspension is stressed, and the tracks are tested under real-world loads. Every vibration, temperature change, and fluid pressure is recorded. The tank then undergoes live fire testing. Operators fire the main cannon at various targets, measuring recoil behavior, targeting accuracy, and reload cycle times. Onboard sensors capture data while technicians observe remotely. Only tanks that pass all mobility, firepower, and electronics tests proceed to the final stage. Once verified, the tank enters final assembly. Crews install exterior components such as camouflage panels, radio antennas, smoke grenade launchers, and field tools. The exterior is painted using infrared deflecting coatings, reducing visibility to thermal imaging. Interior systems like fire suppression, storage compartments, and crew comfort features are finalized. Each tank is then assigned a serial number, recorded in a database for maintenance tracking. Finally, the completed tank is loaded onto specialized transport vehicles or rail platforms and shipped to its designated military unit. What began as raw steel and scrap has now become a fully operational battle tank, a fusion of engineering, firepower, and innovation, ready to defend and dominate in the world's most demanding conditions. Enjoyed this deep dive into how battle tanks are made? There's more where that came from. On this channel, we uncover the hidden engineering behind the world's most powerful machines, from factory floors to front lines, from molten metal to military-grade precision. If you are passionate about how things work, how raw materials become advanced technology, and how innovation shapes modern warfare, hit that subscribe button now and tap the bell so you never miss our next documentary. Your support helps us keep creating high-quality, ad-friendly videos for curious minds like yours. Let's keep exploring the machinery that moves the world.